All right, guys, welcome to 2026. This is officially less than a year left before your HSC and the end of your high school life. You're about to graduate. Now, I understand we didn't quite have the chance to finish the topic, summary statistics last year. So I'm just going to make this into a video, finishing off the shape of distribution and then holiday standard deviation. And then the rest hopefully can be caught up in your own time. And then when we get back to class, hopefully we will be able to move on to bivariate data, which is something that we should be starting today. This term. Now, this is something that you guys may have seen before. The shape of distribution can typically be considered a way of us seeing the distribution of data. The shape of distribution is how concentrated one side of the data is. We typically call that the skewness, how skewed the data is. If it's symmetrical, that means it's evenly distributed, spread out from the center. Everything is evenly spread out. If you can see the quartiles are equidistant from the center, it's nice. So this guy actually has a name. It's called normal distribution. You may not have heard of it yet. Now, in normal and symmetrical distribution, what we can typically assume, approximately, is that the mean, median, and mode are all at the same or very closely similar values. So as an example, if you were to, this is probably the easiest one, if you were to find the mean or the average of this data set, it's going to be exactly the same as the mode, which happens to be the most frequent, and the median, which will happen to be the middle number of the whole data set. This is called the normal distribution. Now, the reason why we do that is because this is actually very common in nature. That's literally it. If you're to have a probability, I don't know if you guys have seen like a little machine that people gamble with, and then you kind of fall into the thing, and it just makes a nice little bell shape. And that applies to any form of population in nature, such as the distribution of height or plague or sizes, whatever happens, it's typically distributed normally, where both ends of the extremes are very few, and then the middle happens to be very frequent or modal in a sense. Now, skewed, when a data is bunched or clustered at one end, it is counterintuitive, but when it's skewed towards the left, we call it positively skewed. This means the lower values, or maybe it's this way to, no, maybe it's that way to you guys. This happens to be more concentrated, and negatively skewed is when it's on the right side. Okay. I personally like to refer to one of the jokes that one of the teachers did. Negatively skewed, this dinosaur called Skewy is looking at the left, and if it's positively skewed, then Skewy is looking at the right. It's positively skewed like that, and this is a tail. Whatever, I don't know. I learned it from another teacher. Okay, so anyhow, box plot distribution. I lost the train of thought. The skew thing was too funny to me. Sorry. Now, you can tell everything is pretty much the same. It's very noticeable if the median, which happens to be the middle line, if you guys remember, if you guys don't remember, that's fine. And that typically tells us what kind of skew this is. If the middle score, which is the 50th percentile, happens to be leaning on the left, that means everything is really clustered here if you were to really put them into a population. Where box plot cannot really show that visually. Okay. Now, typically, this is how we can assume for a normal distribution, as we have discussed earlier, mean and median and mode, they're all same or very similar in value. But a negative skew, when skewy is looking to the left, the mode typically is the most frequent or the highest data in the graph is further on the right, and median happens to be somewhere in the middle. And then the mean, because it gets dragged down by the lowest value, it happens to be a little bit on the left. It's the opposite for the positive skew. The mode, the highest value is furthest on the left. The middle score happens to be a little bit on the right, and the mean happens to be a little bit higher because the very few extremes drag up the mean. So when I say further on the right, I just mean the value is simply higher. So as an example, if I were to talk about someone's height, 150 being the lowest and 200 centimeters being the shortest. Uh, the mode could have been maybe 160, but the median would be 170. And then because of the few people who are 2 meters tall, the average gets dragged up to 175. It's just one of simple, very like, you know, low quality examples. Okay. Now, bimodal distribution is one of the things that we hopefully don't get assessed because it's not that hard. And also, it's like, why bother wasting time? But bimodal just means there are two modes. Bi means two, modal means mode. Okay. Sometimes you can call them trimodal if they have three. Now, comparing data sets is a pretty common HSC question. It's something that you do want to look out for. By the way, I don't know if you guys can read this. Can you guys read that, or is it flipped? Princess on the break. Anyhow, very typical HSC question. They'll give you two box plots or two stem and leaf plots, whatever that might be, and then they say, compare box plot A, voice crack, and box plot B. And they will give you 2 marks to point out two different things. Now, Buzz batteries and never flat batteries are to be compared by testing 15 batteries of each brand until they fail. The lengths of the battery lives are recorded to the nearest hour as shown. Buzz is all that, and never flat is all that. Unfortunately, this is not in ascending order, so we'll actually have to do some work. So let's see. Back-to-back stem and leaf plot. So this is our stem. And then these are our leaves. Let's see. Let's do never flat here, and let's do buzz here. 0, 1, 2, 3. And it seems to be the 30 is the highest we can get. Now, buzz, the lowest one-digit number is 8, 8, and then 9. You guys may skip like 2 minutes from this part of the video, honestly, if you don't want to watch me do this. Just, yeah, it's gonna take a while. I can't edit. So, yeah. 1, 2, 5, 8. Oh, is that it? 9, 0. If you guys haven't skipped and you're still watching this, uh, say say cabbage in class when you see me. That means I'll know you paid attention and you might get a merit. Oh, 2, 6. And I think that's about it. Okay, nearly there. Nearly there. 4, 6, 9. This is what happens when you steal someone else's booklet and then change it up a little bit because some people's workbooks are just so convenient. Same time, I don't have time to make everything on my own. 4, 4, 6, 7. Zero. That's stupid. What am I reading? I think I read the wrong number. 4, 6, 9. Okay, and then 4, 4, 6, 30. 1, 2, 2, 5, 6, 7. Oh, there's another 5. What a sack, right? Compare the median for each brand. Oh, you know what? Let's see. We didn't actually fully answer the first question. Determine which battery is better. Now, you have to think about what the data is actually representing. We are testing the brand until they fail. The lengths of the battery lives are recorded in nearest hour. So it just means whichever one lasts longer is better. What do we want? We want it to be skewed towards the right. This is what we want. We want it to be skewed towards the right, so we want higher values better. And one opposite example might be speed, how long it takes to run 100 meters. We want less time. But this one is the opposite example of that. So we say, oh, this fella has higher value, whereas this fella, the skewy is positive, uh, positively skewed. So we say, yeah, you know what? Uh, never flat is better. It is indeed living up to the name, never flat. Compare the median of each brand. You guys can do that. Compare the mean for each brand. You can do that too. Yeah, yeah. Let's have a look. This describe where the scores are clustered. I didn't skip it because I didn't want to, but I skipped it because I want you guys to try it for yourselves. Describe where the scores are clustered for the girls. I would say around 7 or 8. Now, here's a crucial mistake that I made as Mr. Kim. I didn't actually read the question. I don't know what they're representing. The results for a geography exam are displayed in the back-to-back stem and leaf plot below. The data has been separated into girls' and boys' results for comparison. Obviously, the girls did better because they probably paid attention in class. But let's see. Girls in 80s, boys in 50s. At least it's not a fail. Compare the shape of distribution of scores for the girls to that for the boys. Now, when they say compare the shape of distribution of scores, you actually have to use the keywords. This is very important. You need to say girls scores are what is it? It's leaning towards the higher value, right? It's leaning higher. That means it is negatively skewed. Whereas, what a fancy word. Jesus, English standard, by the way. Whereas the boys scores are positively skewed. Now, at this point, that is just about it. And then you can also say the mode is at 80s and uh, for boys, the mode is in the 50s. You could actually really say that. You know what? I would recommend it in an exam. If it's more than 1 mark, say whatever you can say. Just write it all down. Be safe. Use all the keywords, use all the buzzwords that you've learned in class. Okay. Which group performed better in the exam? Girls or boys? Justify your answer. Girls, because duh. And we can't say that. As higher score means better performance. I like to personally say that because sometimes higher score doesn't mean it's better. Just like the time record for running 100 meters, if you get higher number for that, then it's not really better. So I just like to be clear. You don't have to do it. I just do. Performance. Uh, Girls negatively skewed results display or demonstrate, whatever, any word that makes sense, better score. And what I would also do is refer to mean, median, and mode. Because depending on the exam and depending on the marker, they might really be looking for those numbers instead. Sure, negatively skewed is good. Anyone can see the number. But sometimes an exam might want to assess you on your calculating skills, which to me personally, I think if they want to see that, they should really specify it. But a lot of the teachers do get away just by saying, oh, we said justify, so they should have known. So personally, I want you guys to be safe, I want you guys to do well, and do everything you can. Now, the dot plots, in this case, I don't think it's too hard, so I'm not going to go really intensely into it because also at the same time, I want to go home. I have a lot of other stuff to do for my other classes. Let's see. If you guys have any questions, you guys can chuck me an email, okay? 100%. Parallel box plots, I'm going to do, okay? Two sprinters run the following times in seconds over 100 meters. Sam and Jesse. Find the 5 number summary for each athlete. I'm on a break. You guys can skip it again for like 2 minutes. Well, you can clearly tell it's pretty obvious that Jesse's a worse runner than Sam, but we need to show mathematical reasoning. So, okay, now that we have done the numbers as we can count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This means we need to go for the middle of the two values. So Q2, which is the median, is 10.6. Now, from here, we do the max and min as well, just because we can, 11.5 and 9.9. And at this point, once we have done the median, this actually gets a little bit easier depending on the data. We have gotten rid of the middle one. Now, the first half, we look for the middle, which happens to be 10.3. This is Q1. In the second half, the middle is 11. So Q3 is 11. I'm about to burp. So much coffee. Same logic here. The median is between this. So Q2 is 10.9. Max is 11.6. Min is 9.8. Q3 is 11.4. Q1 is 10.3. Draw parallel dots plots to display the data for both sprinters using the scale below. So let's see. Minimum for Sam was at 9.9, so which is right over here. And then Q1 was 10.3, and then 10.6 was the median, 11 was the this, and then max was 11.5. Meow, 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 meow. Please use a ruler when you're doing this, okay? Anyhow, Sam and Jesse probably should do this because Sam is technically higher up. Now, Jess, adapt, improvise, overcome. Now, max is 11.6, so what the hell? So it goes beyond 11.4. Look how slow this man is. Pathetic, almost. 10.3 and 9.8. Ooh, what do we notice? What do we notice here? What? Well. What have we got here? Find the interquartile range for each other. Well, if you guys remember, IQR is always Q3 minus Q1. So for Sam, IQR, and this is the way I like to do it. IQR, and then small one, Jess. And that would be 11.10.3, 11 minus 10.3, which is 0.7. 11.4 minus 10.3, which is 1.1. Find the range for each sprinter. 1.8. Describe the shape of distribution of times for each sprinter and determine who has better times overall. Now, when they say shape of distribution here, right, there's a few things that I could note. Median. Well, clearly, the lowest record that Jesse had is definitely better than Sam's, but also the worst record is worse than Sam's. It's much more extreme. But at this point, we're not going to worry about that. We're just going to worry about the median. Clearly, the first 50th percentile for Sam is definitely in a lower range than Jesse's is. So we say as Sam's median is lower than Jesse's, we could say it is relatively more positively skewed. It is just, it happens to be a little bit more on the left. Now, oh, oh well. Sorry. And then the spread. Jesse's range is higher. I don't know why I capitalized R, suggesting he is a less consistent runner. Overall, like he's not a very consistent person. He's very extreme. He varies left and right. Oh my God. And so we're not exactly sure how that works. So there's a few of the things that we could argue. Yeah, yeah, that's about it for now. I will bring up some more of the HSC questions or trial papers that I really found interesting using comparing parallel box plots. I just need to figure out which one it is out of the hundreds that I've done before. Probably should have done some work over the holidays. Yeah, well, it is what it is. Now, standard deviation. This is something that I do hope you would remember pretty well from year 10, but oh, it's getting cold. Fan's too loud. Uh, Standard deviation essentially tells us the spread of the data, right? It is important that we know how to do it in a calculator because, well, doing this on paper or formula is just a waste of time. Now, let's see. The standard deviation is a measure of how far scores are spread from the mean. Small standard deviation indicates scores which are closer to the mean and more consistent. As an example, Sam would have a lesser of a standard deviation than Jesse because Sam's are more closer to the center. They're all very concentrated, whereas Jesse's just all over the place, relatively to Sam. Now, the formula for calculating the standard deviation is based on the average of the square of the differences of each score from the mean. I say all that. I genuinely have never actually needed to do this in my life. And I got a band 6 and E4. You do not have to do this. You can just have fun. You can just do your calc, which is slang for calculator, and you just go by your day. There are two different formulae for standard deviation, which result in slightly different values. There's a population standard deviation and sample standard deviation. They're both labeled differently, actually. A population standard deviation is labeled like this. Sample standard deviation is labeled like this. For our work, we'll only consider the population standard deviation. Now, wait a minute. I don't think this is a standard deviation now. Oh, my bad, my bad. Sample standard deviation is this. S. Yeah. I think this is mean. I don't know why I did that. I read the next part and I was like, oh wait, that's where I've seen that from. Anyhow, use your calculator and the instructions provided to find the standard deviation where needed. The maximum daily temperature of two towns are given in tables below. Blah, 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 blah. Now, I personally actually haven't done statistics on this calculator before. I don't know if it's going to be very different though. Yep, single variable. I don't know if the sound of this calculator goes towards yours as well, but it's very meditating. And then, oh my God, this does the whole thing for me. Jeez Louise. Yeah, I'm happy with that. Um, 152 over 7. So that is the same as 21 point something. 20, what the hell? Yeah, 21.7. Something like that. And standard deviation is 4 root 26 on 7, which is R and R on 7, which is 2.9 something. Now, let's have a go at the next data. Inputting data, clear. Oh, this is the only way to do it, it seems. Sorry, guys, I've never done this on this calc. Calc is a slang for calculator. Uh, uh, There we go. 118.07. That's like what? 15.4 or something? What? I am stupid. Can't believe I'd make such a mistake. Um, I apologize. Maybe I'm not qualified to be a teacher. Standard deviation is 2 root 61 over 7. 2.231. Something like that. Now that we have done this, you can say which town has more uniform or consistent daily temperature. Give a reason to support your conclusion. Now, in this case, they're not asking which one is higher or lower. They're just saying more consistent. As GM, Greenmount, has lower standard deviation. In your exam, ideally, actually, like write it out. But I'm being Mr. Kim. I'm being lazy. I'm a princess on a break. This is my fourth cup of coffee. I gotta really stop it. Um, the scores are more concentrated, therefore more consistent. Beep, 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 beep. Low-key, I'm a bit tired. Let's see. Question 2. Peter's results for 3 tests are shown in the table below. Now, this is a very, very, very challenging question because this is year 12, like later year 12 content, but it's kind of like easing you into it. Let's see. Some may argue, oh no, mathematics, I got 65. Oh, maybe I should drop out. so bad at this. But you might think you're better at science. You might think you're so much better in English. You might have to actually think about it, take one step at a time. You have to think about this. From the mean, if I were to draw this out, and then this is the mean, the average. Let's say for maths, 60, and this is what Peter got, 65. What do you notice? Standard deviation, essentially, it's literally how much of a score gap there is that we can expect. That means 2.5 is one jump for a significant chunk of the population. Later, you're going to learn how to actually memorize certain rules about it. But if standard deviation is 2.5, that means from the average, I can do one jump of standard deviation, one standard deviation. Now it's going to be 62.5. And then from 62.5, I need to do another standard deviation jump. And then I finally reach my score, Peter's score. So what does it mean? For maths, this guy is two standard deviations higher than the average. Let's think about it for other subjects, yeah? English, let's say the average was 70, and then average was 60, sorry, 65, and then he was 70. What happens if you were to do a one standard deviation jump? Oh no, it would be 75. One standard deviation jump, which is one standard deviation happens to be 10 marks in English, it would he would be up 75. This means he's only one standard deviation higher than the average compared to everyone in the cohort. Whereas in maths, although the raw score was lower, everyone got 60s and then everyone was very clustered. They all got around 60. It's a very low standard deviation. Everyone was around 60, 62.5, 57.5. It was around there. Whereas English average was 65, but standard deviation was 10. That means a lot of the people got ranging results from 55 to 75 and all around there. Science is the same. It is one full standard deviation away. For maths, it's two standard deviations away. Maths is the highest in comparison to the mean using standard deviation. Again, in your exam, write the full thing. What mark is in the English test is equivalent to Peter's mark in the science test? Now, if you remember, equivalent to Peter's mark in science test, well, he got one full standard deviation higher, right? From average of 70, he jumps one standard deviation, which is 5 marks, and 75. That means from English, he needs to jump up 10 marks, which is one standard deviation. So he would get 75 marks. Okay, so and then what mark in science would be equivalent to Peter's mark in mathematics? It would be two standard deviations up, which is what mathematics was. So it would be 5 times 2, so 10 marks up, which is 80%. Okay. Now, a set of scores has a mean of 10 and a standard deviation of 3. If each score is increased by 5, what effect does this have on the mean and standard deviation? If this is hard, then we must think about it one at a time. Let's think of one example up here. I have, let's see, 8, 9, 10, 11, 12. I have 5 scores. If every score is increased by 5, all that does is it just becomes 13, 14, 15, 16, 17. Notice how the average would have gone up by 5 because every score is went up by 5, but did the spread change? They're all 1 or 2 marks away from the middle. So mean increases by 5, SD remains. Okay. Now I'm going to stop here. You guys should be able to do these sample questions. If you have any questions, just feel free to come by. This is how you use the calc. A little bit of that and here and there. Okay. Now, hopefully that is all good. again, if you guys have any issues, just ask away. You can come by for lunch. I think, oh, actually, yeah, this year I have a bit of a different lunchtime availability, so I'm gonna put that up. Yeah, I'll check. I'll check my timetable again because yeah. Anyhow, have fun, study hard. You're in year 12 now.